inside the millisecond. How a dual-clutch transmission, DCT, really works. In the world of mechanical torque transfer, a fundamental paradox exists. To change the gear ratio, one set of gears must disengage before the next set can engage. In a standard manual transmission, this necessitates a torque interruption, a distinct pause in acceleration where the engine is disconnected from the wheels. Gravity takes over. Momentum bleeds away. The vehicle pitches forward. The torque converter automatics solve this with fluid coupling, but at the cost of direct mechanical connection and efficiency. The holy grail of transmission engineering was a system that could shift gears without a single millisecond of torque interruption. A system where the next gear is already engaged before the current one is released. This is the operational reality of the dual-clutch transmission, or DCT. It is not merely an automatic transmission. It is two manual transmissions expertly nested within a single housing, controlled by a robotic brain capable of predicting the future. To understand the DCT, one must abandon the concept of a single input shaft. The architecture relies on a geometric anomaly, the concentric shaft assembly. The system utilizes two input shafts. One is a solid central rod. The second is a hollow tube that slides over the first, creating a shaft within a shaft. These two shafts operate independently, yet they share the same axis of rotation. The solid inner shaft connects typically to the odd-numbered gears, first, third, fifth, and seventh. The outer hollow shaft connects to the even-numbered gears, second, fourth, sixth, and reverse. This separation is the physical foundation of the system's speed. While the vehicle is accelerating in first gear via the solid shaft, the second gear on the hollow shaft is already pre-selected and meshed, waiting for the command. Connecting these shafts to the engine flywheel requires not one, but two clutch packs. In a dry DCT, used for lower torque applications, these resemble standard friction discs. However, in high-performance wet DCTs, the architecture changes. Multiple steel plates and friction discs are submerged in a bath of transmission fluid. This fluid serves three distinct functions: lubrication, hydraulic actuation, and critically, thermal management. As the clutches slip during engagement, kinetic energy is converted into massive amounts of heat. The oil absorbs this thermal load, preventing the friction material from glazing or warping. Clutch K1 drives the odd gears. Clutch K2 drives the even gears. They are arranged concentrically, with the larger K1 typically surrounding the smaller K2, maximizing surface area for the starting gear. The mechanical hardware is useless without the mechatronic unit. This is the electro-hydraulic command center, located inside the transmission case, submerged in hot oil. It combines a high-processing electronic control unit, ECU, with a complex maze of hydraulic channels and solenoid valves. The mechatronic unit reads data inputs at a rate of thousands of times per second. Engine RPM, accelerator pedal position, wheel speed, and transmission fluid temperature. It essentially builds a predictive model of the driver's intent. If the car is accelerating in third gear, the logic dictates that fourth gear is next. The mechatronic unit sends hydraulic pressure to the shift fork of the even shaft, engaging the fourth gear synchronizer while the clutch for that shaft is still open. This is pre-selection. The shift sequence is a choreographed exchange of pressure. Let's analyze an upshift from third to fourth gear. Currently, clutch K1 is pressurized, locking the engine to the solid shaft third gear. Clutch K2 is vented and open, but the fourth gear ratio is mechanically engaged. When the shift command executes, the system does not simply dump one clutch and grab the other. That would cause a jolt. Instead, it modulates the hydraulic pressure on the pistons, compressing the clutch packs. The pressure on K1 begins to drop linearly, introducing controlled microslip. Simultaneously, the pressure on K2 begins to rise. There is a precise intersection point where both clutches are partially engaged, slipping exactly enough to transfer torque from the inner shaft to the outer shaft without breaking the connection to the wheels. During this crossover, the engine speed must drop to match the gear ratio of the higher gear. In a manual, the driver lifts off the gas. In a DCT, the ECU manages this by cutting ignition timing or fuel injection for a fraction of a second. This torque reduction request is sent to the engine management system. Once clutch K2 achieves full lockup pressure, clutch K1 is fully vented. The transition takes between 8 to 200 milliseconds, depending on the drive mode, comfort versus sport. In sport mode, the slip phase is minimized, resulting in a harsher, faster bang shift that utilizes the rotating inertia of the engine to propel the car forward, actually providing a momentary spike in acceleration rather than a drop. Behind the clutches, the actual gear selection uses synchronizers, similar to a manual transmission. However, these are actuated by hydraulic pistons, not a human hand. A shift fork moves a collar towards a target gear. The blocking ring creates friction between the collar and the gear cone, spinning the gear up to match the shaft speed. Once speeds are equal, the dog teeth can mesh. In a DCT, because the target shaft is not under load, its clutch is open. This synchronization happens effortlessly and silently in the background. If the mechatronic unit predicts incorrectly, for example, if the driver is in third gear and suddenly brakes hard, forcing a downshift to second instead of the pre-selected fourth, the system must abort the pre-selection, disengage fourth, synchronize second, and then shift. This is why a DCT can sometimes feel clunky or hesitate during erratic driving. Where does the force come from? The system relies on a high-pressure hydraulic pump. In older systems, this was driven mechanically by the engine. In modern efficient systems, an electric motor drives the pump, allowing the transmission to maintain pressure even when the engine is off, start/stop technology. The pump generates pressure up to 20 to 30 bar, approximate 400 psi, for the clutch actuation and gear shifting. This fluid is routed through the valve body. Solenoids, acting as gates, use pulse width modulation, PWM, to rapidly flutter open and closed, creating precise analog pressure curves from a digital on-off signal. This fine-grained control is what allows the feathering of the clutch during low-speed creep, simulating the behavior of a torque converter. The Achilles heel of the dual-clutch transmission is heat, specifically in stop-and-go traffic. When a vehicle creeps forward at 5 miles per hour, the clutch cannot be fully engaged, or the engine would stall. It must slip. In a dry clutch system, this slip generates friction heat that has nowhere to go but into the air and the metal mass of the flywheel. If a driver spends too much time creeping uphill or inching forward in traffic, the clutch facings exceed their thermal operating window. The friction coefficient drops, brake fade equivalent, and the mechatronic unit detects clutch kiss point adaptation errors. The system triggers a transmission overheating warning and may open the clutches entirely to prevent catastrophic destruction, leaving the vehicle stranded in neutral until it cools. The most violent expression of DCT capability is launch control. This sequence leverages the unique ability of the DCT to withstand abuse. The driver holds the brake and gas simultaneously. The engine revs to a preset RPM to build boost pressure in the turbocharger. The DCT computer pressurizes the clutch pistons to the exact threshold of contact, taking up all slack. When the brake is released, the mechatronic unit does not gently slip the clutch. It dumps maximum hydraulic pressure instantly, locking the clutch plates together. The shock load is immense, sent through the hardened steel gears to the axles. This achieves the maximum possible acceleration, limited only by tire traction, not human reaction time. Precision comes at a cost. The fluid in a wet DCT is subjected to extreme shear forces and contamination from clutch material wear. Unlike the sealed-for-life myth of automatic transmissions, DCT fluid must be changed. The suspended particles of friction lining can clog the microscopic mesh filters of the solenoids, leading to rough, shifting, or mechatronic failure. Furthermore, the complex dual-mass flywheel, DMF, required to dampen the engine vibrations before they reach the rigid gear sets, is a wear item. The direct connection of a DCT transmits more vibration than a fluid torque converter, requiring robust external damping solutions to maintain cabin comfort. The dual-clutch transmission is a triumph of mechatronic integration. It takes the raw, efficient, mechanical soul of a manual gearbox and fuses it with a digital brain capable of superhuman precision. It solved the paradox of torque interruption by simply bringing a second transmission along for the ride. While it introduces complexity and thermal vulnerability, it offers the only path to shifting gears faster than the blink of a human eye. It turns the driver from an operator of mechanics into a conductor of a digital symphony, ensuring that power, quite literally, never stops flowing.